Hello, in this video we're going to talk about normalization. Okay, so this features a good relation design. So suppose we have combined two tables. So we combine instructor and department into this thing called in depth. Okay, so it represents the natural join on these relations, instructor and department. So as we can see, we have ID, name, salary, and department name, which where I'm guessing are from the instructor table, and department table had department name, building, and budget. So we combine these two tables into one. Okay, so there's some repetition of information, right? Okay, and sometimes if there is no value, we're going to need to use null values. Okay, so decomposition is the only way to avoid these repetition of information in this new table that we created called in depth, right? Okay, so now all decompositions are good. So suppose we have employee, which has ID, name, street, city, and salary. So now we are decomposing this table into two tables, employee 1 and employee 2. So employee 1 table has ID and name, and employee 2 have name, street, city, and salary. Okay, so this might look good, but the problem rises when we have two employees with the same exact name, right? So now this employee 2 does not have a key, okay, a primary key. So next slide shows how we lose information, and we call this a lossy decomposition, okay? So this is the table, original table, ID, name, street, city, and salary, and as we talked about, we are decomposing this table into employee 1, which is this one, and employee 2, which is this one. Okay, so we took ID and name, street, city, and salary for employee 2 table. Now, when we do a natural join between these two tables, if it was lossless, meaning there was no loss, then we should be getting this table, right? But that's actually not the case. Okay, so when we join these two tables again using a natural join, we get this. Okay, so we get ID, name, street, city, salary. So these attributes are the exact same as this original employee. But what happens is we have some loss of information. Okay, so we can see here that we have this ID 57766, Kim, Maine, Rich, and salary is 75,000, right? Okay, and the next one we have the exact same thing, Northampton, but we have a different salary, right? Okay, same thing here. So we have two extra lines of information that were not there before in the original employee table. Okay, so this is what we call a lossy decomposition. Okay, so if we are not able to reconstruct the original table, then that means there was a loss of information. Okay, so what we want is we want to decompose these tables, but we want lossless decomposition where we don't lose any information, no loss of information. Okay. So here we have an example table. This is the original R, okay, and we decompose those into R1 and R2, right? So AB and BC. Okay, and when we take a natural join between these two tables, we get this, right? Natural join. So this is actually exactly the same as the original R. So here we know that we didn't lose any information, and this is a lossless decomposition. Okay, so normalization theory decides whether a particular relation R is in a good form. Okay, so in the case that a relation R is not in a good form, we want to decompose those into two or more relations. Okay, so each of these should be in a good form, okay, and the decomposition process should be lossless, meaning when we take a natural join of all these, relations, we should be getting the original R. Okay, so our theory is based on functional dependencies and multi-value dependencies. We'll go over this one in our class. Okay, so what is functional dependencies? So are usually a variety of constraints on the data in the real world. So for example, our university database, we talked about when we studied SQL, students and instructors are uniquely identified by their ID. So the ID number is unique. It should be unique. So no two students or instructors should have the same ID. Okay, it's a unique ID. Each student and instructor has only one name, so a person does not have more than one name. Okay. Each instructor and student is primarily associated with only one department. Okay, so let's say instructor is teaching at more than one, they still only have only one primary, and the other ones are secondary. Each department has only one value for its budget, okay, and only one associated building for each department. Okay, so these are some examples of functional dependencies. Okay, so let's take a look at this here example. Okay, so this symbol here, we read it as determines. So alpha determines beta. Okay, so we have an example here. Consider a relation R, which has A and B, right? Okay, so B determines A. So does B determine A? So 4 determines the value of A, which is 1, 5, 1, 7, 3. So yes, this holds, right? Okay, and what about A determines B? Okay, 1 gave the value 4, okay, and 1 gave the value 5. So in this case, it does not hold because one should be determining one single value, but here it's giving two different values, 4 and 5, so it does not hold. Okay, so A determines B does not hold. Okay, so closure of a set of functional dependencies. So here, if we have A determines B and B determines C, given these two, we can infer that A determines C. Okay, so the set of all functional dependencies logically implied by F is called the closure of F. And we denote this using this symbol, this plus sign next to F. Okay, so this is the closure of F. So K is a superkey for relation schema R, only if K determines R. Okay, so we have functional dependency allow us to express these constraints that cannot be expressed using superkeys. We have in-depth, which we talked about before, right? We have ID, name, salary, department name, building, and budget. So we can kind of infer, what kind of functional dependencies will hold. So if you know the department name, we can infer, we know which building this department is located in, right? By someone's ID, we can determine which building they are in, okay? Because we know which department they are in. Okay, what about this one? Can department name determine salary? No, because each person in the department have different salaries, so that would actually not be the case. So this does not hold. Okay, so we use these functional dependencies to test relations to see if they're legal under the given set of functional dependencies. So if it is legal, then we say R satisfies F. Okay, so for example, a specific instance of instructor may by chance satisfy name determines ID. Okay, ID, if we know someone's ID and name, of course we can determine ID because we know the ID. If you know someone's name, of course you can get the name. So these are very trivial. You don't really need to put these. These are called trivial functional dependencies.
Okay, let's take a look at the example here. R has A, B, and C. We have two functional dependencies. One is A determines B, and B determines C. Okay, so we want to find out if these, so this is decomposed into R1 and R2. R1 contains A and B, R2 contains B and C. So we want to know if this particular decomposition is lossy or lossless. Ideally, we want it to be lossless. We don't want to lose any information. So these are the steps you take. So you look at R1 and R2 and see what they have in common. It might be one attribute they have in common, or it might be multiple. And with that, we see if we can get either R1 or R2. Okay, so R1 and R2, which attribute do they have in common? So R1 has A and B, R2 has B and C, so we can see that they have B in common. Okay, so with B, we're able to get B. That's trivial, we talked about it, right? So if you know B, you know B. Okay, so this is the notation that you use. The closure, this plus sign means closure. So if you know B, what else can you get using these dependencies? So with B, I can get B, and then using this one, since B appears on the left-hand side, I can get C as well, so I'm going to add C here. So with B, I can get B and C. So we notice that B and C is actually R2. So in this case, this is true, right? R1 and R2, what do they have in common? We are able to get R2, which is B and C. Okay, so we can say that this is lossless. Here is another example where R1 is AB, but R2 in this case is AC. Okay, so what do they have in common? So we have AB here and AC, so we see that we have A in common. So we do the same thing with that closure of A, which we just do A plus equal sign. And with A, obviously, we can get A. That's trivial, right? What else can we get? So we look at this one, and then with A, we're also able to get B, right? So the closure of A is going to be A and B. And A and B can be found in R1. So this first one is true in this case, right? In this decomposition. Okay, so because this is true, this is also a lossless decomposition. And just a side note, B determines BC. This is a shorthand notation. We'll be using that, but this is actually the same thing as B determines the set of B and C. We can also test for dependency preservation. So these are dependencies, right? These are functional dependencies. So in the process of taking the original R and then decomposing it further to different sub relations, sometimes one or more of these dependencies are lost, which is not ideal. We want to be able to, preserve all of those dependencies. So that's something that we should be checking. And here is this dependency preserving. Let's see. So was this one preserved? A determines B? Yes, because A and B are in R1. So this first one was preserved. What about this one? Okay, B determines C, which can be found in R2. So both of these were preserved. This one was preserved in R1, this one in R2. So this is in fact a dependency preserving decomposition. Okay, so A determines B was preserved in R1, okay, because we have A and B in R1, and then this one was preserved in R2 because B and C appear in R2. Okay, so both those were preserved. Okay, so let's see another example. So we had A and B for R1, A and C for R2. So let's see if both of these were preserved. Okay, A determines B, so AB appears in R1, so it was preserved. This one is a little bit tricky. It'll make more sense as we discuss different axioms next week. Okay, so B determines C. We're not seeing B and C here or here, so it's kind of safe to assume that this one was lost. But if we actually look at both of these, if A can determine B, so if you have A, so A, you can get B, right? And if you know B, you can also get C. So we can infer from combining these two that A actually determines not only B, but C as well, right? So A determines C. So that was actually preserved in R2, right? Yes, combining the two, it implies that A determines not only B, but also C, right? So FD2, this one is also preserved in R2. So both of these were preserved, so this is also a dependency preserving decomposition. So let's take a look at this practice problem. So based on what we just talked about, we were talking about two different things, right? One was making sure that it was actually going to be a lossless decomposition, where meaning we're not losing any information. This is what you use. You want to see what they have in common between R1 and R2, and see if we're able to get either R1 or R2 using the closure. And then the other one was dependency preserving. So in this case, you have to check each one of these dependencies to see if we can find that in any of these more decomposed relations. So with that in mind, take a few minutes and take a look at this one. It has R, which has P, Q, R, and S. Okay, and these are our set of functional dependencies. PQ determines R determines S, and S determines P. Okay, and we have decomposed R into R1 and R2. R1 contains PQR, R2 contains R and S. Okay, so we want to see if this is lossless or lossy, and at the same time, we also want to see if we were able to preserve all of these dependencies. So take about like 8 minutes or so. Okay, and then once you're done, you can hit play again. Okay. So let's first look at the first portion, which is if this is lossy or lossless. Okay, so looking at R1 and R2, what do they have in common? So we have P, Q, and R and S. So we have R in common, right? So we take the closure of R. Okay, so with R, you know R, that's trivial. Let's see if we can get anything else using R. This one we cannot use because R does not appear on the left-hand side. This one we can use. So with R, we're also able to get S. So we can get S. And since we know S, we also can get P. So with R, we can actually get R, S, and P. Okay, so R, S, and P, do we see that in R1 or R2? Yes, this one has R and S. So the second one is true where R1 and R2 gives us R2. Okay? So this is in fact a lossless decomposition. Okay, let's see if any of these dependencies were lost. So the first one, this one has a lot of different explanation. I'll just do it kind of the quick way. So actually let's look at this. PQ determines R. So let's see if we can find PQ and R in R1 or R2. So this one does have P, Q, and R. So we know that this first one was preserved in R1. What about R determines S? Okay, we can find R and S in R2. What about S determines P? So yeah, it's easy to say or think that SP doesn't appear here or here because this is missing the S and this is missing P. Okay, so what if we combine these two like we did before in the example? We get R determines P. Okay, so are we able to find R and P anywhere? Yes, we have R and P in R1. So this one is in fact preserved as well in R1. So all three were preserved. We have not lost any dependencies. So it is in fact dependency preserving. This is kind of the long way to do it where you have to go through each possible closure of each possible set of these attributes. Okay, but I will just do it the way I did it. So we know the first one was preserved in R1. Okay, R determines S was preserved in F2. S determines P. This was in fact preserved because we have R determines P.